So the next reaction of group number 16 is reaction with oxygen. As we already discussed, their reaction with hydrogen, they form hydride with the formula H2. Okay, now here these elements form two type of oxides, dioxides and trioxides. Okay, so some points about dioxides, that sulfur dioxide, it is a gas at room temperature. We will discuss about other dioxides such as SeO2, TeO2, PoO2. They are solid at room temperature. Secondly, sulfur dioxide is present as discrete molecule. It means interaction between two SO2 molecule is very weak, that they become free with respect to each other. Hence they are called as a discrete molecule even in solid state. Even in solid state, but other present in polymeric structure, that they exist as long chains of molecules. But in gaseous state, selenium dioxide is present as discrete monomer, in which its structure is similar sulfur dioxide. Okay, so selenium dioxide in gaseous state present as discrete molecule in gaseous state as sulfur dioxide. And if we discuss about sulfur dioxide, then it always present as discrete molecule, either taken in gaseous state or solid state. Okay, now next point about these oxides, they are acidic and basic behavior. So as we know, moving down the group, metallic character increases, and as the metallic character increases, then acidic character decreases. Hence, sulfur dioxide and selenium dioxide, they are acidic in nature. As when it dissolved in water, it gave sulfurous acid. Similarly, selenium dioxide when dissolved in water, it gave selenious acid. So due to the formation of these acids, their nature is acidic. But if we discuss about tellurium dioxide and polonium dioxide, they are amphoteric. Okay, so these are the amphoteric. As amphoteric are those substances which react with acid as well as base. So tellurium and polonium dioxides, they dissolve in alkali as well as acid, hence their nature is amphoteric. Next is about their reducing and oxidizing behavior. So for sulfur, +6 oxidation state is more stable than +4, and in these dioxides, these elements have +4 oxidation state. It means sulfur increase its oxidation state up to +6, hence behave as reducing agent. Now moving down, +6 oxidation state tendency decreases, hence reducing character also decreases. It means if we discuss about tellurium dioxide, then it behave as oxidizing agent. As for this, +4 oxidation state is more stable than +6 oxidation state, hence it is behave as oxidizing agent. Okay, now if we discuss about the structure of sulfur dioxide, then here sulfur has sp2 hybridization with V-shaped structure. How? Write the electronic configuration of sulfur: 2s2, 2p6, 3s2, 3p4, that is 2, 1 and 1. Now in SO2, sulfur has 4 bonds, covalent bonds, hence it also have 4 half-filled atomic orbitals, but in its ground state electronic configuration, it has only 2 half-filled atomic orbitals. To make 4 half-filled atomic orbital, one electron from lower energy orbital jump in higher energy orbital. Here D also present in third shell, but in case of sulfur there is no electron in D orbitals. Hence in excited state the electronic configuration of sulfur is 1s2, 2s2, 2p6, 3s2, 3px1, 3py1, 3pz1 and 3d1. So here it has 4 half-filled electronic configuration in which only 2 half-filled participate in hybridization, leaving behind 2 unhybridized orbitals. So sulfur undergo sp2 hybridization to give 3 hybrid orbitals, in which one having a pair of electron and other 2 are half filled. Okay, so this is the sulfur condition in its first excited state. Here one three pz orbital is as it is, and here the d which involve, that is 3 dz square. It also have 1 electron. These 2 atomic orbitals are unhybridized orbitals. They do not participate in hybridization. So now here sulfur is bonded with oxygen, whose electronic configuration is 1s2, 2s2, 2px2, 2py1, 2pz1. So for this oxygen, one half-filled atomic orbital overlap with sp2 hybrid orbital of sulfur, and other overlap with unhybridized atomic orbital of sulfur. With hybrid orbital it forms sigma bond, with unhybridized orbital it forms pi bond. As suppose this is the sulfur, hybrid orbital, and suppose these are the hybrid orbitals, unhybridized orbitals. Okay, so this become the lone pair on sulfur. This overlap with 2py1 of oxygen atom, first oxygen atom. This overlap with 2py1 of second oxygen atom. Okay, this one overlap with 2pz1 of oxygen atom, and it also overlap with 2pz1 of oxygen atom, and present as sulfur having one lone pair. This one is the lone pair of sulfur, sigma bonded with 2 oxygen, and when these sigma bonds are formed, their p orbitals and d orbitals overlap with each other to form the pi bond. This pi bond is, this one is the 3pz and this is the 3dz square. So this pi bond is called as p pi multiple bond, p pi multiple bond, and this one is the sigma, and this one is called as p pi d pi multiple bond, and this one is sigma. So this is the structure of sulfur dioxide. in gaseous state. Now for trioxides, then all elements involving oxygen form trioxide with formula EO3. Discuss about their physical state. Then ozone, O3, and sulfur trioxide. These are the gases at room temperature, and other trioxides are present in solid state. Now taking the sulfur trioxide, its hybridization is same as that of sulfur dioxide, that is sp2 hybridization with triangular planar geometry. Geometry is different, but hybridization is the same. How it happened? Let us discuss. Here is the sulfur. Its electronic configuration was 1s2, 2s2, 2p6, 3s2, 2px2, 2py1, 3pz1, 3d0. This is the electronic configuration in ground state. Now what about its first excited state? One electron from 3px jump into 3d and it become 1s2, 2s2, 2p6, 3s2, 3px1, 3py1, 3pz1 and 3d1, that is 3dz square. Now it has 4 half-filled atomic orbital, but here if we discuss about its structure, then it has sulfur and oxygen having the multiple bond. Each bond between sulfur and oxygen is the double bond, hence it has 3 sigma bond and 3 pi bond, total of 6. Hence we should have 6 half-filled atomic orbital. For this, one more electron excited from lower energy orbital to higher energy orbital. Now the electronic configuration is 1s2, 2s2, 2p6, 3s1, 3px1, 3py1, 3pz1, 3dz square 1, 3dx square minus y square 1. This is the electronic configuration of sulfur in second excited state. Now we have 1, 2, 3, 4, 5, 6 half-filled atomic orbitals. Now count. If we see here the sigma bonds, as sigma bond are formed by hybrid orbitals. So here the hybridization is again sp2. This orbital hybridized to give 3 hybrid orbital, each having 1 electron. Now there is no lone pair present on sulfur, and 3 unhybridized, each having 1 electron. So they are the hybridized orbital and these are the unhybridized orbitals. Okay, so now this one overlap with 2py1 of oxygen also with 2py1 of second oxygen, 2py1 of third oxygen. As we have 3 oxygen in sulfur trioxide, they form the sigma bonds. And with this unhybridized 2pz of first oxygen, 2pz of second oxygen, 2pz of third oxygen atom overlap to give pi bond formation. So the structure of sulfur trioxide is this triangular shape. If we discuss about its pi bonding, then out of these 3 are sigma. Here first pi bond is between P and P, second is between P and D, third is in between P and D. So it is P pi P pi, it is P pi D pi, and it is also P pi D pi bond. So this is all about oxides. Next topic we discuss here is the oxides, some oxides as O2, O3 and sulfur dioxide. We discuss here their preparation, how they are prepared, what about their structures and properties, physical and chemical properties.